In this video, we're going to be looking at the area formula for circles. We're going to begin by developing that formula, and then once we have that formula, we're going to be extending it to calculate the area of what are called sectors. All right, to develop the formula for the area of circles, which you probably already know what it is. I want to make that point here at the beginning that most likely you already know what the formula for the area of a circle is. But to develop it, we're actually going to divide a circle up into sectors. So each of these little pieces here, which look like a piece of a pie, would be a sector. Okay, so we're going to take a circle. We're going to take that circle, and we're going to cut it into the sectors, and then we're going to move those pieces around so it begins to mimic a shape that we already know to calculate the area for. Okay, it's only going to mimic it because it does have rounded edges. But once we have that put together, we can talk about how we deal with the fact that we actually have these little rounded edges on our sectors. All right, so now I have a whole lot of pieces. I have all my little sectors here. And what I'm going to do is rearrange them. I'm going to move them around so that they interlock with each other. And it's going to look like this. Okay, those two pieces I can put side by side, and they're going to match perfectly because these edge links right here are actually just the radius of the circle. Okay, so I'm going to add another one here. Then I'm going to keep flip-flopping so that they interlock perfectly. And with a little bit of imagination, you can say that that shape looks a little bit like something that we've seen before, which would be a parallelogram. And for a parallelogram, we can calculate the area by multiplying the base times the height. Okay, I'm going to add one more cut here so that I can transition away from a parallelogram and actually to a rectangle. And that cut is going to be dividing this sector in half. Okay, so I'm going to keep half of that sector there, still going to match up with that radius length. And on that end, I can add the other one. Okay, I don't have these laid out perfectly, but when I cut that last sector in half, it does begin to square off the shape that I have here. Okay, so next what I'm going to do is go ahead and glue these down so they look as straight as possible. All right, so here are all the pieces glued down. I didn't do as great of a job as I wanted to. There's a little bit of gaps in the spaces here, but it is starting to look a little bit like a rectangle. If we were to ignore the bumps that we have across the top and the bottom, then it really would look squared off and start to look like a rectangle. So now what we need to do is discuss why these bumps aren't important, because they are part of the shape, right? They're there, but why are they not that important? When I cut this into sectors, I cut it into 8 pieces, okay? I have the choice to cut it into more pieces. In fact, I could cut it into 16 pieces and all the pieces would look just like the 2 that I have here, where I divided that one in half. I could cut them like that, okay? And if you do a comparison of the amount of bump that I have here versus the amount of bump that I'll get on one of those half-size pieces, it isn't as dramatic. If I were to attempt to cut all those off, I'd lose these little pieces, right? Those little parts that are there. But if I were to cut off one of these, that piece is going to be much smaller. Not just half of what I would cut there, but it's not as much overall. That bend isn't going to create as much extra space. So I have a choice. If I use 16 sectors, the bumps will not be as dramatic as I move along, and it'll start to look a little bit more flat. But then I can go beyond 16 sectors. I could do 32, and then they'd have more bumps, but they'd be a lot smaller. Or I could go to 64 or 128, or the idea is that I could take the number of sectors I have to infinity. A point that I can't actually create with paper, but you could imagine would just be so many little bumps here that you wouldn't even notice that they were there, and it takes on that true look of a rectangle. That concept is called limits, and you'll study that later in some of your other math courses like pre-cal and calculus. Okay, so if we accept the idea that we can make this look more rectangular with more sectors, then we can treat the area of this like it were a rectangle. Okay, and that would be base times height. The height here is just the radius of the circle. The base, coming from all those little bumps that we have there, is going to be related to the circumference of the circle. However, this is not the circumference of the circle because half of the bumps are on the bottom and half of the bumps are on the top. So what we actually have is half of the circumference. We've got 1/2, then circumference is 2 pi r. So the 1/2 and the 2, those will cancel out. And then taken from the area formula of a rectangle, the area is base times height. The area here, our base is going to be pi r, our height is going to be r, and we get that the area is pi r squared. The area formula for a circle is pi r squared. For example 1, we are going to calculate the area of this figure shown. This figure is built using a semicircle and a right triangle. We generally refer to these as composite figures. The approach I prefer to use is to create something that I refer to as a shape equation. And that's really just me outlining how I'm going to calculate the area. I'm going to figure out the area of a semicircle plus the area of the right triangle. Okay, and now that might seem a little bit silly to show that, but it does really organize what I want to do. The area of a semicircle is going to be half of the area of a circle, which is pi r squared. So I've outlined that part. Okay, for the right triangle, it's going to be 1/2 the base times height. So in a sense, if I can find values for all of these variables, I'm done with the problem. Everything's outlined for me. It's just a matter of me picking out all those numbers. Okay, the radius is going to be half of this length here, which is shown as a 7. So the radius is going to be 3.5. So we've got 1/2 times pi times 3.5 squared plus 1/2. With respect to the triangle, the base and the height need to meet at a perpendicular, which is going to be here at that spot. Okay, so your base could be this 7, then that 7 could be the height. And if we calculate all of that, that is the area of this figure. All right, so we got 0.5 times pi, and if you do have a pi button, go ahead and use the pi button, times 3.5 squared plus 0.5 times 7 times 7, which of course is also just 49. So I'll just type it in that way. And that's it. The area is 43.74 units, will be meters squared. In addition to figuring out the area of a circle, we can also figure out the area of parts of circles. One particular part is referred to as a sector. A sector is a portion of a circle extending from the center. It just looks like this. You can refer to it as a piece of a pie. Okay, we go to the center of the circle, we draw out a couple of radii, and the region that's in between them here would just be referred to as a sector. To find the area of a sector, you can treat it similar to how we found the length of an arc. And we did that by using a proportion. Okay, and in our proportion, what we did is we took our central angle, the central angle of what would be the sector here. We're going to refer to that as theta in this one. You would take that measurement, place it over 360 degrees. So it's some part out of 360. You then set that equal to the area of the sector over the area of the whole circle, which is pi r squared. Okay, so most likely you're trying to solve for this piece right here. You want to know that, and that would be your x. You would have the central angle that you could put over 360. Here you would calculate the total area. You would then do cross multiplication to figure out the area of the sector. Example 2, let's go ahead and put this into action. We're asked to figure out the area of the sector, which is this shaded region here. To do that, we're going to set up a proportion. The first half of the proportion is going to relate angle measurements. GH, that arc here, has a measure of 72 degrees, which is exactly the same thing as the measure of the central angle that's there. So we're going to place 72 over 360. We're going to set that equal to, let's call this x. We're looking for that area there, so we'll call that x, over the area of the whole circle, which is calculated by using pi r squared, where the radius is 15. Okay, so with cross products, we're going to multiply here, then divide by 360. what I'm going to start with is just calculating this part here. So we got pi times 15 squared. Okay, so the full area of the circle is about 707. We're going to multiply that by 72 to get that number, then divide it by 360, and 141.37 will be the area of the sector. And that'll be in centimeters squared.
Wait, what?